Hello everyone, let's make a start. There may be one or two late stragglers coming in, but we should get going now. So it's a great pleasure to welcome Dan Grimmer here. Dan, of course, is one of our DPhil students in the throes of writing up his term, so it's very good that he's taken some time out of that painful activity to enlighten us, give us some sneak previews of what's going to be going on. So before the DPhil, Dan did the MST with us in philosophy of physics, and before that did a PhD in the quantum information group at University of Waterloo. So has a lot of interesting background in interesting physics and philosophy. And today, if you're bored of the old topology for your space, for your then the answer is with you. We've got the ISE method for new topologies. So over to you, Dan.
Thank you for the introduction. So as Chris mentioned, I'll be taking us on a search for new spacetimes using this ISE method of topological redescription through a bunch of mathematical tools that I've developed in the course of my DPhil year. And you can find these three papers, which are under peer review, and some archive links will be shown at the end of the talk. Or just wait a couple months and I'll show you my thesis. But the subject of the talk is topological redescription. So it's best to start off with just giving an example of this. I'll show something I've come up with called the Mobius-Euclid duality, just as a kind of demonstration of the broadest, what I mean by topological redescription in fairly general terms. Then we'll turn to a more systematic study of these things. I'll introduce what I'm calling space-time representation theory, and then we'll get to the main punchline of my thesis, which is this ISE equivalence theorem, which shows how the sort of scope of topological redescriptions that this ISE method is going to offer us. So we'll have that theorem stated, but then why should we care about topological redescriptions? In the middle, I'll go talk about what are the benefits of mastering our capacity for topological redescription. Then we'll get into some kind of heavy mathematics about homogeneous manifolds. Then we'll review this ISE method and sum up with some conclusions. So it's a lot of content to get through, but let's just jump right into it. So here's our first example of a space-time theory, which I'll show a topological redescription of later. Well, it's not about our world, but it's about some world, maybe. And there's a point-like particle here, and it lives on the Mobius strip, and it just happily floats around, obeying a certain kind of dynamics. If it stays on one fiber, it would oscillate sort of harmonically, like it's in a quadratic potential back and forth there. This is just dynamics I've made up for a theory I've made up, okay? Now, if it's crossing the fibers, it does so at a constant rate and just loops around. So that's a theory. We would describe it with a world line for a particle. It's got some spatial stage it's on. It has some parameter space. Now let me show you what might seem like a completely different theory. Here's a theory no longer about a point-like particle. It's now a line-shaped particle. So it would have a world line in space-time, some other parameter space, but the stage here is the Euclidean plane R2. And it floats around in the plane doing its own kind of thing. One thing it can do is stay parallel to itself and move across this special blue point. Again, kind of harmonic oscillations. Or if it's rotating, it does so at a constant rate. Again, two theories, they seem very different, but they are the first example of topological redescription. There's a sense in which these two theories are nonetheless equivalent. And let me outline how that goes just in rough terms before we formalize it. So there's an isomorphism, it turns out, between the space of all lines in the Euclidean plane and the space of all points on the Mobius strip. They're in a very strong one-to-one correspondence, and that's well known by mathematicians. What I've done is built a space-time theory on top of that to turn it into an example of a space-time duality, or a topological redescription, I should say. Okay, so how's the isomorphism work? Every family of co-parallel lines here in the plane, they correspond to one fiber of the Mobius strip. Every fiber is a family of parallel lines, and the distances between parallel lines is corresponding to the distance between points on the same fiber. Okay, so you capture parallelness and you capture distances. You capture angles as well. Lines on different parallel families or intersecting lines, they would be on different fibers in the Mobius strip, and the angle of intersection corresponds to the distance between the fibers.
So what is a fiber in the Mobius strip?
So yeah, I'm thinking of the Mobius strip as sort of R bundle over the base space, which is the sphere. So this dashed blue line is the base space. I'm thinking it's S1, this is the circle. And every sort of perpendicular section of it is a fiber.
Does it need to be a perpendicular one or just any transversal? Is it all equivalent?
Every base point has one fiber. So every point in the Mobius strip is on exactly one fiber. So, I mean, they don't have to be perpendicular. You can twist them around however you want. But the Mobius strip's divided up into fibers with base points on the base space there.
Sorry, it's the family of co-parallel lines on the Euclidean plane corresponds to what in the Mobius?
One fiber here. So as this red line would explore all of the family of parallel lines out to infinity in both directions, it would move correspondingly here on one of the fibers of the Mobius strip up to infinity in both directions. I've cropped it here so you can see it. It's a Mobius strip of R over the circle with just a twist in it, the standard way you do a Mobius strip. So we're thinking of it, as an R bundle over the circle. Okay. So every fiber corresponds to a family of parallel lines. And you can encode the distances between parallel lines onto it. And you can encode the distance between intersecting lines onto the distance between the fibers. So this fiber is nearer to this one than it is to one all the way around. And we can go into all the details about this. And actually, I will formalize all this in a moment. I'm claiming these two things are equivalent. This captures all of the distances and angles and sense of parallelness that the Euclidean plane has. But you might wonder in this picture, where's the kind of twist? Because the Mobius strip famously has a twist in it, but the Euclidean plane doesn't. So how's that interesting topological feature showing up here? If I took this red line here and I rotated it in the plane by theta equals pi, just around to the other side, it would remain in the same parallel family that it started with, but it would move to the opposite side of the blue point. Right? The same sort of thing happens in the Mobius strip. When you go once around the Mobius strip, this particle would go around, it'd come back onto the same fiber it started on, but it would be on the opposite side of the dashed blue line. That's where the twist is going on. And if for most of the red lines you would do that, you have to rotate by theta equals pi twice to get home. Over here, you have to go around twice for most of the points to get back to where you started. That's not true for the lines here that go through the blue point. The lines are unoriented, so they just have to go around once, and then they're right back where they started. Same thing for the points that start on the blue line. They just have to go around once. Okay, so there's a complete isomorphism, and in fact, an isometry between these two spaces.
So it couldn't be a directed line.
Yeah, it's not a directed line. If you make it a directed line, you
Fails.
get a cylinder here instead of a Mobius strip. Right? Yeah, so another way to see that is if these were directed, you would have a cylinder, but then identifying a line with its anti-directed counterpart gives you the right quotient of the cylinder to turn it into a Mobius strip. That's another way to see it. Right, so we have this interesting example of a topological redescription. And the reason I'm showing this one is partly, as we'll get to later, because it's completely non-algebraic. There's no algebra going on here. But what we've done is we've redescribed this theory in such a way that its background topology is completely changed. It was on the Mobius strip, now it's on the plane. The kinds of particles it's about has completely changed. It was about point-like particles, now it's about line-shaped particles. Basic mereological facts seem to have changed along the way. So this is a really kind of radical kind of redescription when we do these kinds of topological redescriptions. And in general, this will be the case. A lot of things will change as we move from one topological setting to another. Let me just quickly formalize the sense in which these two things are equivalent, because it'll be very helpful to us later. Let's formalize Euclidean geometry in terms of lines. You could do it in terms of points, but given what I just said, let's go with lines. So I'm claiming that Euclidean geometry, in some sense, is going to be exhausted by the set of all straight lines together with their relative distances and angles. And in particular, we can capture that with this sort of quadruple here. We've got a space of all the lines in the Euclidean plane. There's a function that tells us which ones are parallel. When two of them are parallel, there's a function that reports the separation between them. When they're not parallel, they intersect, and we have another function that reports the angle between them. Okay? That's a full characterization of Euclidean geometry. Let me build the same thing here on the Mobius strip. We call 2 points on the Mobius strip parallel when they're on the same fiber. I get to make up whatever words I like. Okay, now we have a function p here that takes in 2 points and reports whether they're parallel in this sense or on the same fiber. There's a distance function for points that are on the same fiber. You can talk about the distance along that fiber. And you can talk about the distance between fibers as well. We have another function that reports for points on different fibers what the distance between their fibers is. Anyway, this is the technical sense in which I'm saying there's an isometry between these two spaces. the space of all lines in the plane with a sense of parallel, distance, and angle is the same as the set of points in the Mobius strip with a different sense of parallel, distance, and angle. There's really a very strong isometry between these two spaces. And like I said, I've built these two space-time theories to be equivalent in light of this isometry that you might know from geometry. How do we see that? Well, space-time theories, as I'm thinking of them, they distinguish between KPMs and DPMs. And in the first theory, on the Mobius strip theory, the KPMs are all the smooth world lines. For the second theory, it's all the smooth world sheets, such that their time slices are infinite straight lines in the plane. Okay? And you can equip them with a sense of parallel, distance, and angle, and such forth, that lets you pick out the dynamically allowed states as a subset of the KPMs, and this lets you write down the dynamical equations. So given that that's what I mean by space-time theories, which I'll repeat in a moment, the two theories are equivalent in the sense that there's an isomorphism between them at the level of kinematics that maps the dynamics onto each other one-to-one. That's the sense in which they are equivalent as space-time, that's the sense in which they're equivalent, yeah. But they display this content on two radically different topological settings. So it's the same kind of structure that's being represented in two different ways. So that's what I'm going to take to be the definition of a topological redescription. So it's two theories that have the same kinematic and dynamical contents. In this case, that there's an isomorphism between their kinematic structures that preserves the dynamics, but they display their two states on radically different kinds of topological settings. And so that Mobius-Euclid example was one, and as I noted before, it's non-algebraic. There's no sum, no product, nothing like that. But here are some more examples of topological redescription. You might start with a theory on some space-time M old here, which is two extended dimensions, space and time, but then two compactified dimensions, S2, okay? You might know that you can redescribe this kind of thing if there was a scalar field on it before. You can redescribe it as a R infinity value field here on a new space-time that loses those two compactified dimensions. And basically what you've done is expanded the field in terms of the harmonic modes of the compactified dimensions. Write down the spherical harmonics, treat them all like they're independent fields on the non-compactified dimensions, and you can redescribe this theory losing its two compactified dimensions. This is a Kaluza-Klein like trick you might have seen before.
So here S2 doesn't need to be small in any sense, as in usual Kaluza-Klein.
No, it doesn't need to be small. No. If it's small, the smaller S2 is, the more massive these fields will be. The length scale associated with S2 turns into a mass scale for these fields. So if this is very, very small, then only the smallest mass modes here will contribute really, and everything else is off in the distance. But if this was a large dimension, then you'd have, just a lot of fields in our sort of mass range. But yeah, this is also a topological redescription. I took one kind of field on one kind of space-time and redescribed it as a different kind of field on a different kind of space-time. Okay, as I'll show later at the end of the talk, we can start with a discrete space-time. So here's like a lattice of points across time. That will be our old space-time. You can redescribe that as being on a continuous space-time. Right? So we're changing the topology, the dimension, the sense of continuity. All of this is up for grabs. And I'll also show a case of Fourier redescription, which is to say the position-momentum duality in quantum mechanics. I'll show that at the end of the talk. All of these are going to be handled by this ISE method in exactly the same way, but I'll talk more about that a bit later on.
Now, can I just ask,
Yep.
in that Mobius-Euclid, I think the dynamics content matching was a quite happily strong claim that it didn't quite matter exactly what the Hamiltonian Lagrange whatever was. Whatever it might be, you could carry it over.
Yeah.
Is that going to be also true in these other examples?
Yeah.
That it's not fortuitous or special to a choice?
It's special that it turns out nice, but it's not special in general, because the way I'm thinking about these topological redescriptions, they're really driven by this isomorphism at the level of kinematics. So this is in bijection with this. This is just a subset of this. Or I think I actually switched them. Anyway, but there's just subsets of there. Given this bijection, there will be some subset which corresponds there. So if all the action's being driven by this kinematic isomorphism, yeah, this just follows along.
The dynamics might look a lot better in one side than the other.
Yeah, in a sense, it might look more or less natural on the space-time, but the way I've defined it, the way that the dynamical states are being picked out from the kinematic states is using these kinds of structures here, these P, D, and A things. Right? I've equipped it with them such that I can write down the dynamics. And I have those analogous objects over here. Right? So I can pick it out in an analogous way on the other side of the picture. So in one sense, it might look worse on the topological staging I'm given, but I have the materials to state the dynamics in the same way. Right? So, yeah, but it might not fit nicely on the new spacetime.
Just a question about dimensionality. Does it generalize to higher dimensions?
Nothing, there's no limit on dimensionality here.
Go from points in R2 to something else, what, lines in R3?
You would,
On the maple strip, you go...
so here, this is based on the fact that the space of all lines in the plane is equivalent to a Mobius strip, but now consider all the space of all 3 sheets in R4. That's some other space. I don't know what it is off the top of my head. It's something Grassmann somethings. I don't know. But any kind of geometric structure, if you look at the space of some kinds of objects in some kind of spaces, you can endow them with a topology, and you'll find out that they are the points of some other topological space. It's a kind of configuration space.
Let's let Dan
go. Anyway, this Mobius Euclid thing is just to give an example. Right? Okay, so we've seen some examples of topological redescription. Now let me move on to the space-time representation theory, and I'll get to the punchline of the thesis in a moment. Okay, so let me just carefully state what I mean by space-time theory. And the sense in which those Mobius and Euclid things are actually inequivalent as space-time theories in the way I'm talking about them. So space-time theories have to make a distinction between KPMs and DPMs. As we saw, they have to have enough structure at the level of kinematics to pick out their dynamically allowed states, but you might want more than that. Like in quantum mechanics, there's an inner product that's very important for its Hilbert space, but actually that shows up nowhere in the dynamical equations. I find that very strange, actually. And we can talk about it later. But you might want those other kinds of metaphysically relevant structures that don't go in expressly to stating the dynamical equations. And lastly, a space-time theory has to pick out a preferred topological staging for its states. So the space-time theory is going to come and say, I'm about this kind of particle on this kind of field, I'm about this kind of field on this kind of space-time, tangent vector fields possibly. Just whatever it is, it has to come up forward and declare itself to be about some kind of state on some kind of space-time. And the Mobius and Euclid theories I just showed, in my language, they're inequivalent to space-time theories because they disagree fundamentally about this third thing. Right? They're representing their states on different kinds of space-times. Right? But they are, in a sense, equivalent. What do I mean when I say they're equivalent? I mean they're equivalent as pre-space-time theories. Still have to make the KPM, DPM distinction. Still have to have this sufficient level of structure at the level of kinematics. But now they're formalized differently, sort of without a preferred topological staging for their states. So this set of kinematical states, we're not treating it like it's a set of maps from some space to some other space. Right? It's not a set of particle trajectories or fields or tangent vector fields or something. Rather, we're going to treat it more like a set of elements with no internal structure, because it's at the level of KPMs that we're doing this bijection. Okay? So we just care about them as sets. But they're in a structured environment nonetheless, so there's a bunch of structure around for them. Yeah?
So very quickly, if you think of the double pendulum as motion on a torus, is it an example as well of
sure.
kind of equivalent as pre-space-time, but not as...
So the configuration space for the torus, would be or for the double pendulum would be a two-sphere. So you could do a topological redescription. Are you describing a pendulum, or are you describing under some kinematic constraints that these are fixed, Or are you describing a point floating around on a torus? That's the kind of topological redescription that I'm suggesting. Yeah. Okay. So these Mobius and Euclid theories, they're equivalent as pre-space-time theories because they're not so committed to the particular kind of topological staging for their states. It's just the structure of the kinematic space and how that relates to the dynamics. So this is what makes them topological redescriptions of each other. Now this brings us to the subject of space-time representation theory, which I'm making in analogy with group representation theory. So group representation theory is about the ways that a certain group structure, say SO3, could be realized as different sets of linear maps on different kinds of vector spaces, some 5-dimensional space, some 7-dimensional space. But we look at all the ways to concretely realize the group theoretic structure in different settings. And if we think of these at G5 and G7 as groups, right, and so we don't look in here to see what kind of particular map this is, then we think that they're equivalent as groups. And if we think of them as group representations, and we care about where they're being represented and how, then G5 and G7 are no longer equivalent. Okay? That's all pretty standard stuff, but I'm suggesting that we do the same thing here for these Mobius and Euclid theories. They are different space-time representations of the same pre-space-time theory. One takes the kinematic structure that they're both representing and represents it with particle trajectories which go from R into the Mobius strip. Another one takes the same structure and represents it as a different kind of thing, these world sheets in the Euclidean plane under some kinematic constraint. Okay? So they're different realizations of the same pre-space-time theoretic structure by being different kinds of maps from different kinds of spaces. That's what I mean by space-time representation theory, and it's tremendously wide, as I think Enrico just pointed out with the double pendulum example, right? It's really a wide space of possible space-time representations we have, and I'm making really no commitments to them having some nice connection with our phenomenal experience of the world or having some nice properties you might expect them to have. I'm just really trying to get all the options on the table in a sense that I'll define later. Okay, so what would we want to do? We'd want to now explore the space of space-time representations. So here's a theory, or just consider some theory about a complex scalar field. It's got some kinematic contents, it's got some dynamics in the kind of sense I was talking about. Now, thought of as a pre-space-time theory, we no longer really care what kind of maps they are. We just want to find different ways of representing this structure, this kinematic structure. And we could look for ways to represent it as point-like particles on some space-time M1, or as line-shaped particles on some space-time M2, or some tangent vector fields on some space-time M3. Like, you could try and represent it in all these different kinds of ways, on all these different kinds of spacetimes. I make no guarantee about the existence or niceness of any particular kind of description. That's for us to explore and find. But first, I'm saying let's get everything on the table, so to speak, and then we'll hone it down with selection criteria later. But let's find a tool that lets us explore this space in an efficient way first. So here is the main punchline of the thesis. The next two slides will be, so ideally we'd have some very strong and widely applicable topological redescription techniques to help us explore this wide space of space-time representations. Here's the space of all possible space-time theories, this big white oval, right? And it's already divided up for us into pre-space-time equivalence classes. You can check that my definition of pre-space-time equivalence, like this condition here, that's obviously an equivalence relation. Okay. So we divide up this space into equivalence relations, and here's all possible representations of some pre-space-time theory or some other pre-space-time theory. Now, this ISE method that I'm gonna tell us about later, it's supposed to help us explore this space of topological representations. It doesn't apply to all of it. It only applies to those that have enough space-time kinematic compatibility. That's a technical assumption I'll define later on in the talk, but it's just a slight limiting of the scope of possible space-time theories we're dealing with. But it's a very weak constraint. So what I do at the end of my thesis is I prove that this ISE relatedness, so whether or not two theories can be redescribed in terms of each other using my ISE method, it's an equivalence relation over the space of theories with space-time kinematic compatibility. So it divides this oval up into equivalence classes. Okay? And so an ISE equivalence class, if you're in the same rectangle here, you can be redescribed as each other via my ISE method. Okay? That's what these ISE equivalence classes are, and we want them to be large in the sense that we want to have a very powerful tool for topological redescription. And that's the content of the theorem. These ISE equivalence classes are as large as possible. So it's not dividing up this space into lots of different rectangles. It is the whole oval. Right? So given any old space-time theory you want, in that wide definition I gave a moment ago, if it has this space-time kinematic compatibility constraint, it's in one of these. And it's ISE related to every new theory which has pre-space-time equivalence, so it's in the same box, and it also has space-time kinematic compatibility. We can explore the entire range of topological redescriptions with this tool that I'm offering. So it's a very general tool for topological redescription. And that's in fact the punchline of the talk. If you just take one thing away, the ISE method applies to a really wide range of space-time theories, and it's supposed to give us access to every possible topological redescription thereof. And its range is only going to be limited by a weak space-time kinematic compatibility constraint that I'll define later on. So that's the scope of the topological redescription tools that I've spent my thesis building. To make it more concrete, let me make a comparison with spacetime algebraicism, which we saw last week in the Thursday seminar. So consider some theory with spacetime kinematic compatibility. It's just my minor technical constraint. It's about some theory about real valued function, right? And it has some dynamical contents and some kinematic contents. But let's, in particular, suppose that the kinematic structure of this theory is a C-infinity algebra in the way that we're used to dealing with for these kinds of Einstein algebras, something like that. What range of topological redescriptions are then available to us? Well, let's limit our search to theories which are also about real valued scalar fields on their new spacetime, whereas we could have explored things about tangent vector fields or particle trajectories. We could have tried to represent it in any number of ways, but let's restrict our search. And moreover, let's restrict our search to spacetime representations of this algebra C-infinity M we want to represent using natural operations on this fine new. So it's normal pointwise addition, multiplication, those kinds of things. So in sum, once we've made these two restrictions, we're searching for a new space of kinematic possibilities, which is itself a C-infinity algebra over some other manifold M. Okay, so these are the restrictions that are necessary to get down to the particular task that the spacetime algebraicist people are working with. And then we can apply this generalized Stone representation theorem that we talked about last week. And it tells us that once we've demanded this pre-spacetime equivalence, and we've also demanded that the new theory is about a real scalar field with its algebraic structure realized as a C-infinity algebra. Together, those imply that the new and old manifolds have to be diffeomorphic, with the relation between the states being the lift of that diffeomorphism. Okay, so that's the general result that we heard about last week. And so the takeaway is that every C-infinity style spacetime representation theory has exactly one nice real scalar field representation of the diffeomorphism. So this is like a unique representation result within a very limited subject, or part of what I'm trying to talk about. But we should contrast this really algebra-heavy example that I just showed you with that Mobius-Euclid duality, which I showed earlier. It has no algebraic structure. There's no sum, there's no product, there's nothing like that. It's a completely other kind of structure which was doing the work for us. But despite their clear differences, this ISE method I'm going to tell you about today, it applies to all these examples in exactly the same way, okay? So I'm not using the algebraic structure to accomplish this topological redescription at all. And in particular, I'm not identifying space-time points as the maximal ideals of certain rings in the way that you might be familiar with. Okay, it's a completely other way of moving between topological representations. And moreover, when we get to the position-momentum duality in quantum mechanics, I'm going to show how we can implement that without thinking of it as a change of basis in Hilbert space. Because again, that's unnecessarily algebra-heavy, and my techniques apply the same way even to these non-algebraic examples. So let's keep in mind that no algebra is necessary for the rest of what follows. Okay. Okay, so what can we expect if we pull off this feat and sort of get these topological redescriptions under our mathematical control in the way that I'm saying that we can? So what if we could remove and replace the topological underpinnings of our space-time theories just as easily as we could switch between different coordinate systems or axiom systems or geometric framings, put those kinds of tools on the table, right? And we can, using this ISE method that I've spent my thesis developing. But what would be the benefits? Well, I argue in the thesis, this is mostly what part one of the thesis is about. We expect similar benefits to those coming from our capacity for coordinate, axiomatic, and geometric redescription already. So I can briefly review what those will be before we get into the details of this. So from sort of least to most ambitious, some expected or realized results, helping physicists with theory development, helping us philosophers understand the epistemic process of theory development, helping us articulate and defend various dynamics-first approaches to interpreting our theories, and helping us characterize potentially the common structure, which is which all of these alternative descriptions are jointly descriptions of. Right? This is from, again, least to most ambitious, and I'll handle them in that order. So for later convenience, I'm going to want to break the epistemic story about how we've come to our theories into two steps. We start with kind of the pre-epistemic world, the noumenal world. I'll make a connection with Kant later. I also call this the dynamical behavior of matter. It's what there is independent of what we think about it, essentially. And then we, in my language, we organize this into our phenomenal experiences. So we apply some unconscious organizational principles to the pre-epistemic world and get to our phenomenal experiences. And then we do the hard scientific work of codifying all those experiences into our formalized theories of physics. Okay, and I call this whole process systemization. Okay, this is just my terminology, but nothing significant hangs on it, I don't think, until maybe a little bit later. Once we have our theories on a table, we want to know, how do our theories come to feature the specific, here's a variable z, which is going to stand for axiom-like laws or coordinates or geometry or topology. But how do those specific kinds of those that do feature in our theories, how do they show up there? Now, in general, our initial z framing of our theory will not be the best one, whatever best means. Right? We found better coordinates for the Schwarzschild solution. Initially, we had a coordinate singularity. We found a better way to do it. Okay? We can search for better axiom-like laws for our theories. Think of something like a Lewisian best systems analysis. He wants our best systemization to have simple axioms, so we have to go search around for simple axiomatizations of our theories. Consider the various geometric reframings of Newtonian gravity, Newton-Cartan, or Maxwell spacetimes. Consider the Einstein-Fokker reformulation of Nordstrom gravity. Consider the geometric trinity for general relativity. Once we have our initial framing of the theory, we like to explore different things. And it's helpful for science, helpful for physicists and for philosophers. And we have the mathematical tools to write down our theories with respect to no coordinate system or any coordinate system, keeping in mind that that's a really wide range, and most of those will be horribly complicated. We can write down our theories with respect to any axiom system we want. This is kind of what theoretical equivalence is trying to explore. And we can use tools from, say, reverse mathematics to show what kind of axioms lead to the kinds of theorems we want. But again, most axiomizations are tremendously complicated. We can have any metric we like or any connection. Again, we can use differential geometry to redescribe our theories in this very, very wide geometric fray. I'll make no promise that any of those are nice, but we have mathematical control over it. And then what I'm offering is we can explore any space-time representation with space-time kinematic compatibility using these ISE methods, but again, most are horribly complicated. So that's kind of moving us from this picture to this picture when we master our capacity for redescription, and then we're going to apply some selection criteria to pick out what are the nice ones, what are the well-structured ones, what are the ones that fit well with our phenomenal experience or what we expect of the noumenal world, any kind of selection criteria you might want. And the benefits are physicists have access to new formulations of their theories, and philosophers are really going to care about this Z selection criteria. Are they objective? Are they conventional? Something like that. But again, I'm trying to get the options on the table first, and then we can really start to have well-structured discussions about that. Okay, so those were the first two benefits, moving from epistemology to metaphysics. Right. So in the laws context, Ned Hall has identified that the unofficial guiding idea behind Humeanism about laws consists in them taking standards that both sides endorse, but that their opponent views solely as epistemic standards, and elevating to the status constitutive of laws of nature. To paraphrase that into what I am saying here, we have laws of nature here in our formalized theories of physics, but where do they get their nomological significance from? What makes them law-like? Right? Is it because they've earned their weight here in the pre-epistemic world by having some governing counterpart that's out there doing law-like work? Or is it because of the epistemic process, the epistemic standards that bring them into our theories? Does that kind of exhaust the nomological significance that they have?
Sorry, then what are the both sides here?
Of the debate, of the Humean and non-Humean. Sorry, yeah. So the Humean in the debate is taking standards that both sides of the debate endorse and promoting them to epistemic standards. So what Hall is saying here is that everybody should actually agree about kind of the epistemics of laws, about how we look at the world, find its patterns, the scientific process that leads to our theories having certain laws. That epistemic story is all agreed upon by the participants of the debate. What they disagree about is the metaphysical status of those epistemic standards. One thinks this is just how we find out about the laws, but the laws themselves are these hardworking things in the noumenal world governing the world. Whereas another view would be that no, they are just exhausted by their epistemic status of how they come into our theories. So that's where Ned Hall locates the disagreement in the metaphysics of laws debate. And I want to take that and generalize it to these other aspects of our theories. So again, we have here our epistemic story. The laws acquire their nomological significance kind of along the way rather than by having some hardworking counterpart that does work at step 0. So it's about how they earn their nomological significance. And I'm going to call this style of views dynamics first views about any Z. And the third benefit of mastering this kind of topological redescription or any kind of redescription is in helping us articulate these kinds of dynamics first views. Here's my statement of a dynamics first view, which you might associate with Lewis, although there's a lot of other variations of this that count as well. So our theory's laws don't gain their nomological significance. The theory's laws are here. Right? They don't latch on to any dynamics facilitating, hardworking stuff in the noumenal world that's giving them their metaphysical oomph. Instead, they acquire their nomological significance only along the epistemic route because they're a particularly nice way of systematizing the noumenal world. Systematizing is what takes us from the noumenal world to our theories. And I should point out that this is compatible with realism in a sense. The laws can be real in the sense that they're objective and mind independent without them doing any governing work. So the question's not about realism here. Okay, compare that dynamics first view of laws I just said with its sort of originator, the Humean view of causation. I would take Hume to say that our phenomenal experiences of causation here, they don't gain their causative significance by latching onto any hardworking cause-effect relationships out there in the world. What they're doing is they acquire their causative significance only because they're a particularly nice way of organizing the world. But what does Hume in particular mean by particularly nice? He would say that they're customs or habits which compel our mind to move from cause to effect. So he gives a story about what makes them nice and how they pick up their causative significance. Okay, let me skip over that one. But here's this dynamics first view of geometry, which I'm thinking of along the lines of the kind of Harvey Brown stuff that a lot of us are interested in working on. Our theory's geometric structures don't gain their geometric significance by latching on to any hardworking geometric stuff out there in the noumenal world. Rather, it's sort of via this epistemic process of being a particularly nice way of systematizing dynamics that they earn their kind of chronogeometric significance. I take that to be a fair summary of the geometric side of this debate, or the dynamical side of that debate. But I want to extend that to space-time topology here. And so the claim would be that our theory's space-time doesn't gain its spatiotemporal significance by latching onto any hardworking noumenal stuff out there in the world. No space-time points, so not like Newton. No space-time relations, so not like Leibniz. It's a different thing. I'll show you what it is in a second. But instead, our spatiotemporal significance of our space-time manifolds only comes because they're a particularly nice way of systematizing the dynamical behavior of matter, which we're going to think of somehow pre-space-time, theoretically. That may sound a lot like a Kantian view of space-time, and I think it is. Here's what Kant would say about space and time, is our phenomenal experiences of space and time don't gain their metaphysical significance by latching onto any noumenal points or relations. Instead, they gain their significance because they're a particularly nice way of organizing the noumenal world. And what does Kant mean in particular? They're a priori prerequisites for the very possibility of human experience. That's what Kant would say. You can disagree with him about that while keeping the rest of the view. Okay, so it's structurally a kind of Kantian view.
Sorry, wait, are you equating the second sentence in parentheses with the previous sentence?
No, they're not equivalent. No, sorry, the thing in brackets is what Kant would say to articulate what particularly nice means. So these kinds of dynamics first, whatever views I'm talking about, they've got this big hole in them. What's particularly nice mean? You get to fill that in. It's a style of view which locates the source of the metaphysical significance in the epistemic path rather than in the kind of noumenal path. Okay? So this is in particular what Kant would say in spelling out his view, but my view doesn't have that bracket at the end, and you're allowed to think whatever you like about what makes these things particularly nice. But it's a Kantian style view, in a sense I hope is clear enough. Okay, I promised 4 benefits, so all those 3 benefits I talked about before, you can actually achieve them, I argue in my thesis, without putting any particular doctrine about what's going on here in the noumenal world. You don't have to say much about that, but you might want to. So suppose that we're a realist and we've been convinced that some aspect Z of our theories is reflective only of the representational process that brings it into our theories, rather than reflecting any hardworking stuff here in the noumenal world. You're of course then motivated to look to this thing that's the result of mastering our capacity for Z redescription. You look to our Z-free or Z-invariant formulations of our physics for a picture of what's going on in the noumenal world, if you want to be a realist about it, right? And you can do that, and that's benefit for getting mastery of this kind of redescription helps us inform what that picture of the world might be like. Okay? So in review, we can help physicists with theory development. We can better understand the epistemic process of theory development, articulate and defend these dynamics first approaches to our theories, and maybe even characterize the common structure that all of these alternative descriptions are descriptions of. I mean, it's very ambitious to get to the end of that list, but these are hopefully helpful techniques along the ways for people who are interested in those kinds of things. Okay.
We've got about 20 minutes left.
Yeah, I'll get there on time. So I'd be happy to talk about all that later. And the goal of my thesis is to take this stuff about laws and geometry and extend it to space and time. Now we're going to get to a pretty mathematically heavy portion of the talk. And if you lose your place at this part, don't worry, I'll pick you up again when we come to section 5. We need this tool called homogeneous manifolds to do the work for the ISE method. So let me just introduce them briefly. So what is a homogeneous manifold? It's homogeneous with respect to a Lie group which acts transitively on it. What does transitive mean? It means any point on the manifold here can be mapped to any other point via some group action from this H group. Okay? So any point can be mapped anywhere by some application of H. Just to give you some examples, the sphere is homogeneous with respect to the rigid rotation group. Any point could be mapped anywhere, North Pole to South Pole, North Pole to equator, whatever you want. The plane is homogeneous with respect to the R2 addition group. The plane is also homogeneous with respect to the special Euclidean group. Here's a surprise, the Mobius strip is homogeneous with respect to SE2 as well. Okay, so lots of different manifolds are homogeneous with respect to different groups. A non-example, let me skip over that. So we can construct homogeneous manifolds, and this will be important for later, by taking the quotients of Lie groups. The quotient of SO3 by SO2 is the 2-sphere. I don't know if people have seen that. You might have, and this one's trivial. The quotient of this addition group by the trivial subgroup is the plane. The quotient of SE2 by SO2 is the Euclidean plane, or the quotient of Poincare group by the Lorentz group is the Minkowski space as well. Okay, so you should be familiar with those things. The quotient of SE2 by the Euclidean 1 group turns out to give the Mobius strip. That's surprising. Okay, so in general, when you take the quotient of a Lie group by any closed Lie subgroup, it yields a smooth homogeneous manifold with respect to the group in the numerator. Now, you can use this to represent Lie groups as diffeomorphisms. So pick any two pairs of Lie groups and take their quotient, with the square brackets going to mean the coset, the G2 coset. So the group in the numerator has a kind of natural group action on the space of cosets. It acts on them by applying its group action before we take the quotient, essentially. But what this does, it takes our Lie group here, which didn't have to start off as diffeomorphisms, but it represents them as diffeomorphisms on the new spacetime. Okay, they have a natural way of being represented that way. And this representation is going to be faithful if and only if the quotient's already in lowest terms. Okay, if there were any non-trivial normal subgroups of G1 inside of G2, then there would be a cancellation and it interferes with things. So we're always going to assume we're working in lowest terms. Okay.
G2 doesn't have to be normal in G1.
No, G2 does not have to be normal in G1. Just the opposite. It has to be anti-normal. It has to contain no normal subgroups. If you took the quotient with a...
It isn't about the quotient group. It's about an action on the quotient set.
If you take the quotient of a group with one of its normal subgroups, you end up not just with a manifold, but with another Lie group. We're dropping that. So in general, this space MG is not going to be a Lie group. Like you can get the sphere out of it. Right? So SO3 by SO2, not a normal subgroup. You just get a manifold, not a group. But in general, when you take quotients of Lie groups, you get manifolds. And if they're in lowest terms, then the numerator group is faithfully represented as diffeomorphisms on the quotient space. Right? And it turns out all homogeneous manifolds can be built in this way. If you start with a homogeneous manifold, it comes with a transitively acting Lie group by definition. Put that group in the numerator. Now look up the stabilizer subgroup of that group action. That's the group, that's a subgroup of the big group that fixes a special point. So pick some point P0, find all the diffeomorphisms or all the Lie group transformations that leave P0 at P0, That's the stabilizer subgroup. Put that in the denominator. And by the previous slide, the quotient is a homogeneous manifold, MH. And it turns out by some mathematical wizardry that that is always the manifold you started with. So M was our original manifold. We looked up its diffeomorphisms, put them together in a quotient in a certain way, and we've reconstructed the manifold up to diffeomorphism. And this always happens. So up to diffeomorphism, the space of all homogeneous manifolds just is the space of Lie group quotients. They're the same thing. What this means, and this is how we build into the ISE method, if you pick two Lie groups, it uniquely picks out a homogeneous manifold in the following way. You're thinking of a manifold M. I don't know about it, but you give me two clues. You say there's two subgroups. The subgroup H1 is SO3 and it acts transitively. The other subgroup is SO2 and it's the stabilizer of that group action. Now you've told me everything about your spacetime, or your manifold, I mean. So up to diffeomorphism, there's one possibility. You have to be thinking of the two-sphere, okay? And R2 is the unique thing that has a transitive SE2 action stabilized by SO2. And the Mobius strip is the unique thing that has a transitive SE2 action stabilized by E1. You can just pick out homogeneous manifolds by Lie group actions in this way. So now suppose I have a favorite Lie group G1 and a favorite closed lowest term subgroup of it. I can make the following two demands and pick out a unique smooth manifold. G1 is going to be faithfully represented as a transitively acting group of diffeomorphisms. Right? And G2 will be its stabilizer subgroup that uniquely picks out the quotient manifold of them up to diffeomorphism. So we can just make these declarations that certain Lie groups will act transitively on our new space, and we build the space thereby. So we can uniquely specify a smooth manifold by declaring that G1 will act transitively on it, and G2 will be its stabilizer subgroup. This is the method we're going to use to build new spacetime manifolds when we use this ISE method.
Homogeneous.
Homogeneous ones, yeah. Just technical point, everything I mentioned here only works for finite dimensional Lie groups, but I'm working on some math results that extend it to infinite dimensional Lie groups, and then you can build much, much more. Okay. But we're going to build homogeneous manifolds in this way. And I can also use these techniques or an extension of them to build fiber bundles and spinner bundles and whatever you like. But I don't have that published yet. But these kinds of techniques, building things out of Lie group quotients, is extremely general. So what's this ISE method? So given some space-time theory you present to me, I'm first going to de-emphasize its topological staging, which could have been a Mobius strip or the Euclidean plane, roughly by thinking of it as a pre-space-time theory in the sense I was talking about before. And we have enough structure there to, at the level of kinematics, to pick out the dynamically allowed states. All well and good, but you might expect that we lose topological information about the old manifold in the process, right? We've forgotten that the particular states we're dealing with are states from some manifold to some space R, and we completely forget about M old, you might think. But surprisingly, a theory spacetime manifold will actually faithfully survive internalization if it meets this spacetime kinematic compatibility assumption that I've been mentioning throughout the talk.
What is internalization?
I forgot to mention this ISE method. It's a three-step process. So it's the first step in the process. You first internalize the theory, which is sort of to forget about its old spatiotemporal setting. Then we're going to search around for new spacetime settings, and then there's a process to build them, which is the externalization. Forget about spacetime, search for new spacetimes, build your new spacetime. That's the three steps. Sorry, I should have said that. Okay. So once we've forgotten about the spacetime, you might think we actually, forget about the spacetime. That's what I said it does. Right? But actually, if you look more closely, the spacetime manifold actually faithfully survives this kind of internalization process if it has spacetime kinematic compatibility. What does that mean? It's a very, very minor assumption. I hope you'll agree. But the first thing is it has to be kinematically reduced. Technical assumption, it means that only the trivial diffeomorphism, d equals 1, lifts to act trivially on every kinematically allowed state. So if we have some d star and we lift it to act on some state sigma and it returns sigma and it does that for all kinematically allowed states, then it has to be the identity diffeomorphism. Yeah.
What if there are no unique lifts for the?
So right. So this is a constraint that I had in a footnote earlier, but I didn't mention it. I have to be on a natural bundle so I can have kinds of lifts. But as I mentioned just a moment ago, I'm upgrading these tools so they work with fiber bundles. So I can build a fiber bundle space using the quotients of 3 different Lie groups, and then I get all these lifts for free because I've constructed the whole fiber space. But yeah, I have to be on a natural bundle at the moment, but I'm working on extensions where that's not a limitation.
But this natural bundle comes from a mere pre-spacetime theory.
No, we're applying.
We're in the full glory of the spacetime theory.
Yeah, we're in the full glory of the space-time theory at the moment. The internalization process takes in a space-time theory. It's going to spit out a pre-space-time theory. Okay, but we've taken this as input.
KC on the spacetime theory. Okay.
So I'm showing. Yeah, so it's the space-time theory that has space-time kinematic compatibility, not the pre-space-time theory. Right. Anyway, so we lift the diffeomorphisms, and in general, they act non-trivially on at least some state. It's only the identity that acts trivially. That's a very weak assumption. And here's the homogeneous assumption. There has to be some, again, it's finite dimensional, but I'm working on removing that Lie group, which acts transitively on the manifold. So it has to be a homogeneous manifold, but also this group has to preserve the theory's kinematic constraints. Right? So it has to lift to act on kinematically allowed states to produce other kinematically allowed states. But if it does that, then the whole thing has space-time kinematic compatibility. Yeah, and I'm working on generalizing this to make this assumption even weaker. Okay, assuming we have this space-time kinematic compatibility, you can reconstruct the old space-time manifold as a quotient of Lie groups, like I showed before. Right, now, define H star to be the lifts of these diffeomorphisms, because again, we're in a natural kind of setting where that's possible. The manifold is still the quotient of these lifted diffeomorphism groups. But these lifted diffeomorphisms are just Lie groups acting on S-kin old. Now, they happen to be the lifts of diffeomorphisms, but as Lie groups, if you forget that fact, there's still perfectly good Lie group actions on the states. And this makes sense from a pre-spacetime theoretic perspective. And so I'm going to call these two Lie groups that come out of this, call them pre-spacetime translation operations. This is the main building block for a new spacetime setting. And that, we could use that to recover the old spacetime setting as well. So in the second step of this ISE method, you search around for new pre-spacetime translation operations. They don't have to be the ones I just showed, and I'll show some examples and sketch a definition later on. But the new and the old theory that we're redescribing here, it's going to differ about which PSTOs qualify as spatiotemporal. And once we have these PSTOs picked out, you're going to use them to build a new spacetime manifold. And it's the unique spacetime manifold where whatever Lie group actions you chose on the theory states, it's the unique place in which they become honest-to-goodness spacetime translations. In the sense that I talked about on the previous slides. We uniquely specify a smooth manifold by declaring that some Lie group action will be faithfully represented as transitively acting diffeomorphisms, and a subgroup of that will be faithfully represented as the stabilizer subgroup thereof. That uniquely picks out the quotient manifold as the space we're talking about. So given some pair of Lie group actions on the theory states, you make these demands and thereby uniquely construct a new spacetime setting for the theory. And contrast that with the method of building manifolds from spacetime algebraicism, which was the maximal ideals of rings. Yeah.
Sorry, I think I missed. What's up? Where do these Lie groups come from? They already have smooth and topological structure themselves.
Yeah.
What is their importance? Why are they more important?
Yeah. I'll show some examples in a moment that'll motivate why we're doing them. But I'm just this is just an overview of how the process works. I'll show some examples that motivate them in a moment. But they are the seeds of a new spacetime setting. We have our space of states, which we're thinking of divorced from any particular topological staging. There are Lie group actions on that huge, huge space of states. I say, I like those ones. Make those ones spatiotemporal. I'm giving you a tool that does that, right? So anything, and they will be then lifts of diffeomorphisms on the new spacetime. So any Lie group actions which are consistent with that kind of construction, if you give them to me, I can build the spacetime setting where they are spacetime translations. They're whatever you want them to be, given certain constraints that I'll talk about in a moment. Right? And then we build a new spacetime from them in which they are honest-to-goodness spacetime translations. Very different from spacetime algebraicism. So in the second step of externalization, we have this new spacetime M, and we have to map the new states onto it. And I'll show an example in just a moment where the task of mapping the states onto the new space-time is actually forced on us, and we have really no freedom in how that happens. And to see that, yeah, let's implement a Fourier transform using these PSTOs. Right. Oh. Back. Okay. Okay, just a very quick aside. That group in the denominator is required to be in lowest terms with the group in the numerator. And so if the group in the numerator is abelian, then all of its subgroups are normal. And this G-fix thing can't contain any non-trivial normal subgroups, so it's forced to be the trivial group. That's just a little fact. So when we're dealing with an abelian group of transformations, it actually seems as if our PSTOs are just one Lie group and not two. Okay, so that I'm just going to talk about one group of PSTOs here. Okay, so here's a theory about some states, and we have these PSTOs which just shift the state in its old space-time. Okay, these are the lifts of diffeomorphisms, in fact, and they qualify as pre-space-time translation operations. I'll show a definition in a moment, but they just happen to be the lifts of diffeomorphisms. Not all Lie group actions on the theory states are the lifts of diffeomorphisms in the old space-time setting. For instance, these Fourier shifts aren't. Take a state, apply a Fourier shift to it. That's not a lift of a diffeomorphism, but it is a Lie group action on the states. But if you think about the theory from a pre-space-time theoretic perspective, I don't know what space is and what Fourier space is. I just know there's a Lie group action on my states, and it looks a hell of a lot like a space-time translation. And it is this translation somewhere in Fourier space. What I'm saying is we can build Fourier space from those Lie group actions. And this is in general what the definition of a pre-space-time translation operation is. They're any pair of Lie group actions on the theory states which are in a sense structurally indistinguishable from space-time translations. They are the space-time translations of some topological representation of the theory. That's not how I define it, but that is effectively a definition. And I prove that that property holds. Okay, so these Fourier shifts are structurally indistinguishable from space-time translations. Here's a little video of them. That doesn't look like a space-time translation, but if you didn't know what space and time were, it would look like one. And here's how it acts on the state. But of course, that's to shift the state in Fourier space. That's just what we want the new space-time to do. We want to build a new space-time from these things such that these are the space-time translations. And when you externalize these, it uniquely constructs a new manifold here. And effectively, this is a copy of the old theory's Fourier space. I don't have time to go into the details now, but when you try and move the states over from the old space-time to the new space-time, there's exactly one way to do that, and it's via a Fourier transform. So we build the new space-time, move the states over, and it all follows naturally from our choice of pre-space-time translation operations. And so from this perspective, let's look at some quantum harmonic oscillators here. Here's a harmonic oscillator here with a cosine-shaped potential. Here's one with a weird non-local coupling term, this hyperbolic cosine of a derivative. And here's one set in Hilbert space. Now, I can translate between all of these three things using these PSTOs, and it's not via a choice of basis that I understand them as being different. In particular, each of these theories externalizes what the old theory calls translations in space and time to get to the old theory, translations in time and Fourier space. You say, I really want these to be my space-time translations, and you end up building a space-time where that's true. And translations in time alone would give you a kind of Hilbert space picture of the theory. And this Mobius-Euclid thing can be handled in the same way without any algebra. I'm just picking Lie groups, declaring that they're the new space-time structure, and they are.
You've got to put some odd terms in each of those Hamiltonians in those three equations,
yeah,
right?
right.
So there's a sense in which the conventional Fourier transform between position momentum representation is completely regardless of the Hamiltonian. Can you just walk me through what is the relationship between these three, this slide, especially line 3 of it, and elementary textbook thinking? Because we don't see any specification of H in the elementary textbook.
So these things here in the brackets, that is the Hamiltonian for the theory in all three cases. So it's a linear operator that's self-adjoint and acts on the space of states, which is structured like a Hilbert space in each of the three cases.
So this is, I agree, these are QHO theories by declaration by you. But this happy equivalence is not as general as the elementary textbook Fourier transform, which is independent of any choice of Hamiltonian.
Yeah, so what I'm doing is independent of the Hamiltonian as well. I mean, well, if you had a different Hamiltonian, the Hamiltonians would be different. But the transformation is the same. We're just regarding what was the position basis in one theory as the momentum basis in the other via a Fourier transform. We can talk about this more at the end of the talk. But it's just by declaring that what you used to think were Fourier shifts to be new space-time translations, you automatically get this new framing for the theory. Just one last quick example, and then we'll get to some conclusions. So inspired by Achim Kempf, he has this great paper called Space-Time Could Be Simultaneously Continuous and Discrete in the Same Way Information Can Be. But how is that possible? Building on Kempf's work, I applied, well, a much earlier version of the ISE method to this example. Here's a theory on a lattice about some heat distribution where it's all localized here at the moment. But you can translate that around in space here. These are discrete space-time translations, right? And we have them, obviously. But this theory also, and all lattice theories, admit continuous pre-space-time translations, which I'm about to show you. These funky transformations I'm showing here, they interpolate between discrete space-time shifts in a special way. And just like the Fourier transformations, those don't look like, oh, might have frozen. Anyway, okay, those don't look like space-time translations in the old theory, but from a sort of pre-space-time theoretic perspective, they could be space-time translations. They have the right kind of Lie group structure to be like that. And so here's some now two-dimensional lattice theory. We've got some distribution of heat at one time and at a later time. I can use those continuous PSTOs I just showed you to build a new space-time setting for the theory through this kind of Lie group quotient construction, such that those funny transformations I just showed you literally are the new space-time shifts in the new theory. So that weird combination of shifting the state around, which wasn't the lift of a diffeomorphism, that literally becomes a space-time translation in the new framing of the theory. And I build it such that that's the case by the kinds of Lie group action declarations that I've been talking about. And it turns out that this is also a symmetry of the theory. So, I mean, these continuous shifts are also a symmetry of the theory in addition to the discrete shifts for certain kinds of theories. Okay, I'll wrap up quickly with some conclusions. I've introduced a kind of space-time representation theory about taking the structure of our theories at a kind of kinematic level and representing that as about different kinds of space-time, about different kinds of functions and particle trajectories on different kinds of spacetimes. I showed some examples to show how wide this kind of catalog of topological redescriptions are. We had the Mobius-Euclid duality, this Fourier position momentum duality, this discrete to continuous representation, the dimensional reduction thing I showed earlier, Enrique's example about the double torus and the double pendulum, I mean. Right? And what I'm claiming is that we can approach these topological redescriptions systematically, like we did with coordinate transformations and reaxiamizations and geometric framings. We have all of this under pretty well mathematical control, at least how to move between the theories. What the landscape looks like, there's a lot of good work to do there. And the punchline is that this ISE method applies to a very wide range of space-time theories and gives us access to effectively every possible topological redescription thereof, just limited by this weak kind of space-time kinematic compatibility constraint, which I'm working on making even weaker in future work. But what epistemic questions come up from all of this? We can try and explore more systematically the range of topological redescriptions that are available to us, and we can focus in on what are the selection criteria, given all these possible ways of topologically framing our theories. Which one do we actually go with and why? What's our selection criteria for these things? An easy answer is that it should align with our phenomenal experience of space and time, the manifest kind of space-time that's around us. But does it really have to? You might be interested in space-time representations of your theories which don't align well with our experience of the world. For instance, consider something like an ADS-CFT-like duality. You could have the bulk. We all think we live in a 3+1 dimensional bulk space-time, but the real action's happening on the boundary. And somehow that's where the fundamental stuff is going on. Right? So you might be interested in alternate topological representations of your theory for these reasons. Or why did our spatiotemporal intuitions pick up on the particular space-time framings that they did? Was it locality or symmetry or low dimensionality? I mean, we can start to explore which of these is actually the deciding factor. And and what topological framing is best outside of our phenomenal experience. So we all see the world as macroscopically 3+1 dimensional, but if there were compactified dimensions, do we want to include them in our physics, or we could do this topological redescription to get rid of them at the cost of adding a bunch more field content? Same thing here, the discrete and continuous things. At a macroscopic level, they look the same. Right? We get down to the microphysics, we have a choice, it seems. Do we want to put it on a discrete lattice, or do we want to make it a band-limited field on a continuous spacetime? That seems to be a choice of topological redescription we have, independent of phenomenal experience. Or do we want to put our supersymmetric physics on a supersymmetric spacetime or not? All these are examples of topological redescription. A few of them are outside of my scope at the moment, but is our topology selection criteria objective or conventional in these regimes?
Sorry, for band limited, you mean there's a UV and an IR cutoff?
I'm just a UV cutoff. Yeah, so when you do this discrete to continuous redescription, it ends up with a band-limited theory. I forgot to mention that. But that's a very important thing. But you could always represent things in this way. Right? And so are they objective or conventional? How do we come to pick the particular one that we've come to pick? Turning to kind of metaphysical questions, where in our epistemic story does our space-time manifold acquire its spatiotemporal significance? Right? We have some space-time in phenomenal experience, we have some space-time in our theory, but where do they get their spatiotemporal oomph from? Is it because there really is some kind of spatiotemporal stage or relations out there in the world which are doing important metaphysical work and which they've latched onto? Or do they earn their metaphysical relevance along the way by being a particularly nice way of systematizing dynamics? We could be more or less Kantian there, but it's a Kantian kind of style view. One thing I'd like to talk about in the discussion, if we can, I think the space-time algebraicism that maybe we heard about last week, it was compared with a Leibnizian approach to space-time. To me, by my lights, it looks much more Kantian. So I'd love to talk about that. Okay. And finally, let's suppose that we do want to be realists, and we're convinced that this space-time manifold's reflective only of the representational process rather than any underlying noumenal stuff. What's it helping us represent then? If we go in this direction, I think we're led to a kind of structural realism, which could be ontological or epistemic, and the world kind of hangs together as a seamless structured unity, at least as far as we can tell. And we have lots of different pre-space-time structure for our thing, but it's a set of elements, the way I've formalized things. Right? And then we project the kind of representation onto it. Most of those are horribly complicated in this wide field, but some of them are nice, and maybe our intuitions via some evolutionary process, perhaps, have picked up on some nice one. And this is why we see the world in the spatiotemporal terms that we do, not because it fundamentally is spatiotemporal. Okay. Thank you for your attention, and I'd love to have any questions.
Well, let's take our break there and then reconvene at 1:15.